Hello students, welcome to Adi Chemistry's online coaching. I am Aditya Vardhan from adichemistry.com Warangal. In today's session, we will explore the fascinating world of molecular vibrations and discuss how to determine whether they are infrared active or not. This topic is crucial not only for exams like NTA, CSIR NET, GATE and IIT JAM, but is also valuable for university level competitive exams. For more in-depth study material and video presentations that will help you excel in these exams, I highly recommend visiting adichemistry.com. Let us dive in. The molecular vibrations are broadly classified into two types, stretching and bending. Stretching involves a change in bond length without affecting the bond angle. Bending, on the other hand, results in a change in the bond angle. It is important to remember that during bending vibrations, there may be slight adjustments in bond lengths to maintain the center of mass of molecules. Both stretching and bending vibrations are further divided into specific categories, which we will explore in more detail. Let us begin by looking at the simplest type of vibration in a homonuclear diatomic molecule. It is a stretching vibration without change in the dipole moment of the molecule, making this mode IR inactive. One should remember that for a vibration to be IR active, there must be a change in the dipole moment during the vibration. In the case of a homonuclear diatomic molecule, the dipole moment is initially zero, and since no dipole moment is altered during the stretching motion, the vibration does not interact with the infrared radiation, making it infrared inactive. Let us now consider a heteronuclear diatomic molecule where the smaller atom is more electronegative than the larger one. As a result, the molecule has a dipole moment with the negative end pointing towards the more electronegative smaller atom. When the bond undergoes stretching, this dipole moment changes. Since a change in dipole moment is necessary for a vibration to absorb infrared radiation, the stretching mode becomes IR active. Now let us consider triatomic molecules. The stretching vibrations can be either symmetric or asymmetric. Let us start by looking at symmetric stretching. Consider a linear triatomic molecule with two identical atoms bonded to a central atom. Each bond has its own bond moment. But since the bonds are identical and the bond moments point in opposite directions, the molecule has no overall dipole moment. In a symmetric stretching mode, both bonds stretch by the same amount but in opposite directions. As a result, the net dipole moment of the molecule remains unchanged during this vibration, making it IR inactive. Now let us examine a symmetric stretching in a non-linear triatomic molecule. Even though bonds are identical, the angle between them results in a net dipole moment represented by the green arrow. Since this is a symmetric stretching, both bonds undergo stretching simultaneously and to the same extent. However, unlike in linear triatomic molecule, the net dipole moment does change during this vibration. Consequently, this symmetric stretching is considered infrared active. Now let us examine what occurs during asymmetric stretching. In this mode, the stretching vibrations do not occur simultaneously. Consequently, there is a change in the net dipole moment of the molecule during these vibrations. As a result, this asymmetric stretching mode is classified as infrared active. This explanation is also valid and holds true for both linear and non-linear molecules. In case of non-linear molecules also, the dipole moment is changed, hence it is also infrared active. Here is a special case of an asymmetric triatomic molecule. In this scenario, the stretching is asymmetric because the atoms connected to the central atom are different. Consider this hypothetical molecule. The bond moments are unequal, resulting in an initial net dipole moment. During the stretching vibrations, the dipole moment changes, making this mode IR active. It is important to note that even if both bonds are vibrating simultaneously, the magnitudes of their stretches are not the same. The bond associated with the smaller atom experiences a greater stretch than the bond with the larger atom. Therefore, the stretching mode is classified as asymmetric. Now let us explore bending vibrations. Consider a simple bending vibration in linear triatomic molecule. Recall that in bending vibrations, the bond angles are altered. In order to maintain the center of mass of the molecule, the bond lengths are also slightly changed. In this mode, the bond moment changes during the bending motion, resulting in an alteration of the dipole moment. Therefore, this bending vibration is classified as infrared active. For other nonlinear and more complex molecules, the bending vibrations can be further categorized into several interesting modes like wagging, twisting, scissoring, rocking. Let us walk through these vibrational modes one by one. The first one is wagging. Here, the two atoms connected to the central one move together in a coordinated manner by swinging back and forth on either side of a central atom. The bond angles change, but the atoms move together in the same direction away from and towards the central atom, almost like the motion of a dog's tail. This change in bond angles and movement of the atoms can alter the dipole moment, often making wagging vibrations IR active. This is twisting. It is a type of bending vibration where two atoms move in opposite directions relative to each other, creating a twisting motion around a bond axis. Twisting vibrations can alter the dipole moment depending on the molecular structure and are often IR active as a result of the changes in molecular geometry during the motion. This is scissoring vibration. Here the two atoms or groups move towards and away from each other, similar to the opening and closing of a pair of scissors. This vibration occurs in a plane where the bond angle between the two atoms or groups changes. Scissoring usually causes a significant change in the dipole moment, making this mode infrared active. And finally, the rocking mode. In rocking vibrations, two atoms or groups move back and forth in the same direction, resembling the motion of a rocking chair. The atoms move parallel to each other with little or no change in bond length or bond angle. Rocking vibrations may or may not be infrared active. It is also important to mention that the total number of vibrational modes for a molecule is determined by the formula 3n-5 for linear molecules and 3n-6 for non-linear molecules, where n represents the number of atoms in the molecule. That's all for now. Visit adichemistry.com for more information on this topic and notes for CSIR NET, GATE, IIT JAM and other university level examinations. And don't forget to like, share and subscribe. All the best.